When we say nothing, we imagine an empty void. No stars, no planet, no space, no time. But in physics, the kind of nothing doesn't exist. Even what we call a vacuum, deep, empty space is not truly empty. It is filled with fields, energy, and fleeting particles that appear and disappear in the blink of an eye. This is the quantum vacuum, a restless sea beneath reality, invisible to us, but fundamental to everything that exists. Here's the strange part. In quantum mechanics, uncertainty rules. Particles can borrow energy from nothing as long as they return it quickly enough. These are called virtual particles. They are constantly flickering in and out of existence, like tiny ghosts haunting the fabric of space. If you could somehow strip away all matter, all radiation, and even all light, you would still be left with this quantum vacuum. A nothing that is, in fact, something. This raises an unsettling thought. If the vacuum is always seething with activity, then maybe the Big Bang was not the birth of something from nothing, but simply a fluctuation of this ever-present energy, one that, for reasons we do not yet understand, did not vanish and instead became our universe. Philosophers have wrestled with this idea for centuries. In philosophy, nothing is the absence of everything, no being, no properties, no laws. But in physics, there may be no such thing. What we call nothing might just be the lowest possible state of something. So when we ask, why is there something rather than nothing, we might already be starting from a false premise. Perhaps there was never a choice between something and nothing at all. Perhaps nothing was never on the table. And that thought changes the question entirely. If there was always something, energy, fields, laws, then the mystery is not how the universe began from nothing, but how and why it began from that something. It is here, standing at the intersection of physics and philosophy, that we realize the question of before the Big Bang is not just about the universe. It is about the limits of the human mind, because maybe, just maybe, we are trying to see the edges of a picture. We are trapped inside. Throughout history, nearly every civilization has tried to answer one question. Where did the world come from? In ancient Greece, the poet Hesiod wrote in Theogony, the universe began in chaos, a formless void, from which came earth, and the gods themselves. In ancient India, the Rigveda declared, in the beginning, there was neither being nor non-being, no air, no sky, only the one, a seed of everything, or perhaps a kind of cosmic consciousness. In Chinese legend, the universe was once an unbroken cosmic egg. Inside it slept Panyu, who awoke and split it apart. The light rising to form the heavens, the heavy sinking to become the earth. Different myths, same instinct. They refused the idea of absolute nothingness. Instead, they imagined some kind of something. Chaos, a god, a seed that existed before everything else. And in a strange way, this is not so different from the problem modern science faces. We too find it hard to accept the idea of the universe appearing from truly nothing. Our minds want to believe there must have been something there first. For centuries, the dominant view, even among scientists, was that the universe was static and eternal. Stars lived and died, but the cosmos itself had no beginning, no end. Even Albert Einstein favored a universe that simply was. That began to change in the 1920s. Belgian physicist Georges Lemaitre proposed that the universe began as a primeval atom, an unimaginably dense point, which suddenly began to expand. The idea was met with laughter. British astronomer Fred Hoyle, in a 1949 radio broadcast, mockingly called it the Big Bang. He meant it as an insult. The name stuck anyway. What turned the joke into serious science was the work of an American astronomer named Edwin Hubble. In 1929, using the Mount Wilson Observatory's giant telescope, Hubble made a discovery that changed everything. Wherever he looked, galaxies were drifting away from us. And the farther away they were, the faster they moved. This could mean only one thing. Space itself was stretching. If you ran time backward, all those galaxies would collapse into a single, impossibly dense point. The universe had a beginning. Hubble's observations were the first major evidence for the Big Bang. The second piece of evidence would come 3 decades later, from an ancient light still echoing through the universe today. If Hubble's discovery was the first clue, the second came not from a massive telescope or a decades-long mission, but from a pair of engineers chasing a mysterious hiss. The year was 1964. Honor Penzias and Robert Wilson were working at Bell Labs in New Jersey. Their task? Just a large, horn-shaped antenna, originally built for satellite communications. It was supposed to detect faint radio waves from space. But there was a problem. No matter where they pointed the antenna, no matter the time of day or the season of the year, they heard a persistent, low-level noise. It was the hum of electronics. It was interference from nearby cities. They even climbed inside the antenna to clear out what they thought might be the cause, a nesting pair of pigeons. And, well, the mess pigeons leave behind. Still the hiss remained, the constant faint static. It was everywhere, and it was identical in every direction. What Penzias and Wilson didn't know was that just 40 miles away, a team of physicists at Princeton University was looking for exactly that signal. They believed that if the Big Bang had really happened, the early universe would have been unimaginably hot, a sea of radiation so intense it could strip electrons from atoms. As the universe expanded and cooled, that blinding fireball would fade. Its light stretched into invisible microwaves over billions of years. If such a glow still existed, it would be the afterimage of creation itself, a fossil light from the moment the first atoms formed. When the Princeton team heard about the noise from Bell Labs, they realized it was no accident. Penzias and Wilson had stumbled upon the cosmic microwave background, the oldest light in the universe, released just 380 years after the Big Bang. To put that in perspective, if the entire history of the universe were a single year, that light began shining on January 1st. And Earth wouldn't appear until December 31st at 11:59 p.m. The discovery was a smoking gun for the Big Bang theory. It told scientists that the universe was just expanding. It had once been hot, dense, and uniform, before gravity and time sculpted it into the cosmic web we see today. And here's the eerie part. That ancient light is still around you, right now, in the space between you and your screen. In the air around your head, microwave photons from the dawn of time are passing through you. They've been traveling for nearly 14 billion years, and they will keep going long after you're gone. But as clear as the CMB was, it didn't answer the bigger question. Yes, the Big Bang happened, but what triggered it? To answer that, scientists had to go even further back, into a fraction of the first second, where the laws of physics themselves begin to break down. Let's try something impossible. Let's rewind the universe. Galaxies rush back toward one another. Stars collapse into clouds of gas. Atoms break apart into subatomic particles. Everything space, time, matter, energy, compresses into a single, blindingly dense point. We are now in the Planck era, but time so early, so extreme, it lasted only 10 seconds. That's 0.00000000000000000 or 0.0000000 1 seconds after time began. If you blink, you've already skipped it. In fact, if you try to imagine it, you've already failed. Because even our best physics stops working here. Why? Because this is where two great pillars of science, general relativity, Einstein's law of the very big, and quantum mechanics, the law of the very small, collide and fall apart. General relativity says space minus time bends and curves under mass and energy. Quantum mechanics says particles and energy jitter and fluctuate at the tiniest scales. In the Planck era, the universe was so hot and dense that these two laws must work together. And yet, they don't. It's like trying to use two different maps to navigate the same terrain. and discovering that neither of them matches the ground you're standing on. We don't yet have a theory of everything to unite them. String theory, loop quantum gravity, these are ideas, but we haven't proved any of them. Still, scientists can make educated guesses. They believe the newborn universe was a quantum foam, a seething, churning blur of energy, where particles popped in and out of existence, and space minus time itself rippled, like the surface of boiling water. Then, something happened. We don't know what. It could have been a quantum fluctuation, a random blip in that foam that didn't fade away. It could have been a phase transition, like water suddenly freezing into ice, only on a cosmic scale. Whatever it was, it unleashed an event we call cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded faster than the speed of light, not because objects were moving through space, but because space itself was stretching. Imagine a balloon inflating from the size of an atom to the size of a galaxy, all in less time than it takes light to cross a single proton. Inflation smoothed out the chaos, flattened the geometry of space, and scattered quantum fluctuations across the cosmos, tiny seeds that, billions of years later, would grow into galaxies, stars, and planets. When inflation ended, the energy driving it transformed into a flood of particles and radiation. This was the hot Big Bang proper, the moment when the universe became the fiery, expanding sea we often imagine when we hear the name Big Bang. From there, the universe cooled, allowing quarks to bind into protons and neutrons into atomic nuclei, and eventually, after hundreds of thousands of years, electrons to settle into orbits, forming the first atoms. But even if we can describe what happened in those early fractions of a second, we still face the ultimate mystery. Why did it happen at all? Inflation may explain the how, but it doesn't explain the why. To find that answer, some scientists began asking an even more dangerous question. Was the Big Bang truly the beginning, or was it just the latest chapter in a much older story? So far, we've traced the story of the universe back to its earliest measurable moments. But now, we're about to step into forbidden territory, a place where our equations lose meaning, where every answer raises a dozen new questions. What, if anything, existed before the Big Bang? It's tempting to picture a ticking cosmic clock and imagine winding it back past zero. But zero is not a wall. It's a cliff. When we step over the edge, time itself falls away. And yet, physicists can't resist the question. Over the past few decades, they've imagined several possibilities. First, the cyclic universe. One idea is that the Big Bang was not the first bang. Instead, the universe might be trapped in an endless loop, expand, slow down, collapse, and explode again. Each cycle wipes the slate clean, but perhaps leaves faint traces, subtle patterns in the cosmic microwave background, a ghostly memory of universes past. It's a poetic vision. Our universe is just one heartbeat in an eternal cosmic rhythm. But current evidence suggests our universe's expansion is speeding up, not slowing down, which could mean no future collapse, and no next cycle. Second, the multiverse hypothesis. Another possibility: the Big Bang wasn't a unique event at all. Instead, our universe might be just one bubble in a vast, foaming sea of universes, each with its own laws of physics, its own version of reality. In this view, inflation didn't just happen once. It's happening all the time, somewhere, budding off countless bubble universes like sparks from a fire. If this is true, then asking what happened before the Big Bang is like asking, what happened before this wave in the ocean? The answer is there were other waves, and there will be more. The catch? We may never be able to see beyond the walls of our bubble. The other universes, if they exist, are forever beyond our reach. Hawking's no-minus boundary proposal. Stephen Hawking offered a different answer, one that challenges our very idea before. He suggested that time itself could be curved, like the surface of the Earth. On a globe, there's no point north of the North Pole, not because the North Pole is special, but because north simply stops making sense there. Likewise, in Hawking's model, the Big Bang isn't a point in time you can go before. It's the edge where time begins, and beyond it, the concept of earlier simply doesn't exist. It's a hard idea to wrap your mind around. Our brains are wired to think in timelines, causes and effects. But here, cause and effect may be illusions born from within time itself. Fourth, the quantum creation hypothesis. And then there's perhaps a most unsettling thought of all, that the universe simply appeared. In quantum mechanics, the vacuum isn't truly empty. It teems with fleeting particles and energy, popping in and out of existence, borrowing energy from nothing as long as they give it back quickly enough. What if our entire universe was just such a fluctuation, a random blip in the quantum void that didn't fade away? If so, then nothing was never really nothing, and the Big Bang was not a miracle, just a statistically improbable event in an infinite amount of time. The truth is, we don't know which, if any, of these ideas is correct. Maybe the Big Bang was the beginning of everything. Maybe it was just one chapter in an endless story. Or maybe the question before the Big Bang is one the universe itself refuses to let us answer. What we do know is this: whatever happened, if anything, before time began, set the stage for everything we see, everything we are, and everything we may one day become. And that leads to an even deeper mystery. Why is there something rather than nothing at all? When we say nothing, we imagine an empty void. No stars, no planets, no space, no time. But, in physics, that kind of nothing doesn't exist. Even what we call a vacuum, deep, empty space, is not truly empty. It is filled with fields, energy, and fleeting particles that appear and disappear in the blink of an eye. This is the quantum vacuum, a restless sea beneath reality, invisible to us, but fundamental to everything that exists. Here's the strange part. In quantum mechanics, uncertainty rules. Particles can borrow energy from nothing as long as they return it quickly enough. These are called virtual particles. They are constantly flickering in and out of existence, like tiny ghosts haunting the fabric of space. If you could somehow strip away all matter, all radiation, and even all light, you would still be left with this quantum vacuum. A nothing that is, in fact, something. This raises an unsettling thought. If the vacuum is always seething with activity, then maybe the Big Bang was not the birth of something from nothing, but simply a fluctuation of this ever-present energy. One that, for reasons we do not yet understand, did not vanish, and instead became our universe. Philosophers have wrestled with this idea for centuries. In philosophy, nothing is the absence of everything. No being, no properties, no laws. But in physics, there may be no such thing. What we call nothing might just be the lowest possible state of something. So when we ask, why is there something rather than nothing, we might already be starting from a false premise. Perhaps there was never a choice between something and nothing at all. Perhaps nothing was never on the table. And that thought changes the question entirely. If there was always something, energy fields, laws, then the mystery is not how the universe began from nothing, but how and why it began from that something. It is here, standing at the intersection of physics and philosophy, that we realize the question of before the Big Bang is not just about the universe. It is about the limits of the human mind, because maybe, just maybe, we are trying to see the edges of a picture. We are trapped inside. If the Big Bang was the beginning of time, then what will be its end? The answer depends on one thing: how the universe's expansion behaves in the far future. For much of the 20th century, scientists assumed gravity would eventually slow the expansion. If there was enough matter in the universe, its own gravity could pull everything back together in a big crunch, a reversal of the Big Bang. It would be the ultimate cosmic heartbeat. Bang, crunch, bang, crunch forever. But, in the late 1990s, astronomers discovered something unexpected. The expansion of the universe isn't slowing down, it's speeding up. Something we now call dark energy is pushing space apart faster and faster. We don't know what it is. We don't know why it exists, but it makes up roughly 70% of the total energy in the cosmos. If dark energy remains constant, the universe will keep expanding forever. Galaxies beyond our local group will drift so far away that their light will never reach us again. Stars will burn out. Black holes will slowly evaporate. This is the heat deaths in area, a universe that ends not in fire, but in eternal, frozen silence. There's also a more violent possibility. If the strength of dark energy increases over time, the expansion will become so extreme that it will tear apart galaxies, then star systems, then planets, and finally, the atoms themselves. This is called the Big Rip. It would be the end of everything: space, time, matter, and even the quantum fields that hold them together. And yet, there's one more possibility. What if dark energy is not permanent? What if it fades, allowing gravity to take over again? The universe could still collapse into a big crunch, and in that final, crushing instant, conditions might be identical to those of the Big Bang, triggering a new explosion, a new universe, and a new cycle. If that happens, our Big Bang would be just one chapter in an endless cosmic book. The truth is, we don't yet know which ending awaits us. The universe could die quietly, or violently, or be reborn over and over. What we do know is that, for now, we are living in the middle of the story, in the brief, bright moment when stars shine, planets form, and life can wonder about where it came from. We began with nothing, or at least, what we thought was nothing. We've traveled from the myths of ancient civilizations, to the telescopes that revealed an expanding universe, to the cosmic microwave background, the oldest light we can see. We've plunged into the first fractions of a second after the Big Bang, and even dared to ask what might have come before. Along the way, one truth has emerged. The universe is not what our instincts tell us it is. Time is not a straight road stretching forever in both directions. Space is not a silent emptiness waiting to be filled. And nothing is not an absence. It is a stage, a restless backdrop, from which the play of reality can suddenly begin. But for all we have learned, the central question remains unanswered. Did the Big Bang have a cause? Was it inevitable, or was it a cosmic accident? And if it was not the first, how many universes have come and gone before ours? The universe offers us clues. The faint hiss of ancient light, the accelerating drift of galaxies, the patterns in the large minus-scale structure of space. But it also withholds the final page. Maybe it always will. Perhaps the human mind was never meant to see beyond that first moment. Or perhaps we are still in the opening act of a much larger story, one that will only reveal its meaning billions of years from now. And yet, there is something quietly profound in the fact that we can even ask. Somewhere in this vast, expanding space, on a small blue planet orbiting an ordinary star, creatures made of stardust have begun to wonder where it all began. That curiosity, that desire to know, is itself an echo of creation. Because whether the universe is a single act or an infinite cycle, whether it began from true nothing or from something we cannot yet name, we are part of it. We are not outside observers. We are woven into its fabric, and maybe that means the universe has been asking about itself all along, through us. So when you look up at the night sky, and you see the light of stars that died before Earth was born, remember this. You are looking at the aftermath of an event so ancient that time itself began in its wake. And perhaps, in the silence between those stars, the echoes of creation are still traveling outward, waiting for someone, somewhere, to listen.